Today we're going to talk about linear programming. In order to discuss linear programming, we first need to define 4 vocabulary words. Please feel free to stop this video at any point in time so that you can get the information that you need. So the first word is linear programming itself. Linear programming is that process or technique that we use in order to find solutions to linear inequalities or situations. In doing this, we're going to optimize. That means to maximize or minimize some equation in the process. That might be profit, it might be expenses, it might be area of a box or something, but there's some equation that defines what we're doing. That equation is called the objective function. So it's the equation that we're trying to maximize or minimize. It's, like I said, it's cost or profit or area or whatever we're trying to do. So it's an equation. It has an equal sign. The next thing are constraints. The constraints are the inequalities that we use in our situation. That's what defines what we have available to use. We've called them restrictions in the past. So any kind of limits that we put on anything, those are our constraints. The feasible region is the area of the graph where we find the solutions to our problem. So any possible combinations of answers are found in that area of the graph. You ready to try some? In this first example, we're going to find the values of x and y that minimize the objective function. And as you can see, I've listed some things here for you. So right here, these are your constraints. Okay? These things, those 4 inequalities, are our constraints. Down here, this C, that's our objective function. Okay? So what we have to do now is we have to first graph all 4 of our inequalities. And to do that, you can see each one is graphed on this graph here with different colors. So the red, the first one, y plus x is greater than or equal to 8. That's this area here. The blue, the x plus y greater than or equal to 20. So that's this area here. Okay. We have x is greater than 0. So that's this green area. And then the orange area, y greater than or equal to 2. Okay. So we graphed them all. Our feasible region is defined by the vertices here, and that's this area here. Okay? This area up here is where all 4 of our inequalities are graphed. They're covering that area. So the brown muddy area is where our feasible region is. The vertices, we need to check each one now in our objective function in c equals 3x plus 4y in order to see which one minimizes that number, that cost or that c value. When I do that, you can see this vertex here is 0, 8, so that's my first one. So 0, 8 is here. Then we have 5, 3, that's this one right here. 5, 3 gives me 27. This last vertex is at 10, 2. And when I substitute that value in, I get 38. So each of my vertices, that's where I'm going to find that optimized value, in this case the minimum. And you can see that at 27, that gives me the minimum value. So that means that whatever x stands for, I need 5 of them. Whatever y stands for, I need 3 of them in order to get the minimum value. Okay? One last one. We have a word problem. So Bob the builder is building tool sheds. He uses 10 sheets of drywall and 15 studs for a small shed and 15 drywall and 45 studs for a large shed. He has available 60 sheets of drywall and 135 studs. Bob makes $390 profit on a small shed and $520 on a large shed. So how many of each kind of shed should he build to maximize his profit? So something to think about as we are maximizing his profit. One technique that I would use for this is I would set up all my important information in a table of values. I'm not going to do that here, but that is one technique to organize yourself. So put your small shed information in one column, your large shed information in another column, and your total in another column. Make lines for your drywall and your studs and your cost. And then you've got everything set up. Once you do that, you can see X represents this number of small sheds and Y the number of large sheds. You get your constraints like this. So 10x plus 15y is less than or equal to 60. 15x plus 45y less than or equal to 135. I have the x is greater than 0 and y is greater than 0 because I can't have negative sheets of drywall or negative studs. Okay? So those are my constraints. The objective function comes from the money. So I'm talking about my profit, $390 profit on a small shed, $520 on a large shed. So we want to maximize his profit using that objective function. So we're going to graph them. Graphing the situation looks like this, and you can see where all of those, sorry about that, where all of those come together. This is our feasible region. Okay, so in this area is our feasible region. Looking at the feasible region, we now analyze for our profit. We need to look at our vertices. Our vertexes are at 0, 3, 3, 2, and 6, 0. I also have one down here at 0, 0. But 0, 0 will not give me a maximum, so I'm not even going to test it. In order to test them, we're going to put those back in the objective function. If I substitute those values into the objective function, I get a profit of 1560, 2210, and 2340 respectively for each of those three vertices. Okay? Now I want to maximize my profit. So maximum profit is here at 2340. That tells me that Bob should sell 6 small sheds and no large sheds, since the X value has to do with the number of small sheds and the Y value has to do with the number of large sheds. I hope that makes sense. Please continue to work on some of these on your own. Try to organize yourself when you're writing your constraints and your objective function, and bring any questions to class.